Okay, so return 10.5. Now, P0 actually requests none earlier on, but right now it requests the full one, 4.3, and it's definitely enough. So when you return the 0.0. So we do P4. So finally available is plus 0.0 because it actually did not acquire anyone. It acquired P3 immediately from here, enough. And then finally it returns 0.0. You get back 10.5. So you find out that this is the sequence where it is safe sequence or safe state. Okay? So when we assign the process, we have to assign it like this. Alright? That means the operating system says, okay, since I can find the safe sequence, now I can allow this guy to acquire 1.0. Okay? So does it approve this request from P3? P3 request for earlier on requested for 1.0. Is it granted? Yes. Why? Because we have a safe sequence P1, P3, P0, P2, P4. The operating system is sure that no deadlock is going to happen. Then it's going to grant this P3. Yes, I can give you this. You understand? So why is it called banker's algorithm? Because it do accounting. Just like you go to bank, right? You're going to find out whether you've got enough debit, credit, and all that, right? So here is the same thing: debit, credit. Do you have enough money? If you have enough money, yes, I can borrow to this guy first, this guy in sequence, and this is a safe sequence. So I can lend to all of them this much of resources, and they are going to be happy and no deadlock. Is that clear? Yes. No. Okay. Why is it no? Because if you want to run at the same time, you need 25. Remember, the maximum 7, 3 plus 9 plus 2 plus 4 is 25 resources. You must have 25. Then only you can run them at the same time. But in this banker's algorithm, we try to minimize this total available. We want to find, if let's say we have this much, can we find a safe sequence? And this safe sequence will only allow one process to run until completion. Okay? Right. So that is just an assumption. It's just an assumption because you see, when I do this analysis, I'm thinking the banker actually think of the worst case. You just want to find whether this is safe sequence, but actually you want to grant only 1.0. You see that 1.0? This is just a mental, mental scenario that the banker think of the worst case, because this is the worst case that can happen. Okay? If this worst case you still survive this worst case, that means I assign 1.0 to you. You understand? To answer your question just now, maybe I did not make it clear. Yes, you can run them in parallel. After the operating system grant you 1.0, you can run in parallel, no problem. But this is the sequence where the operating system needs to make sure that it is safe. That means there's a safe path and there's no deadlock. Okay? So when the operating system grant 1.0, now P0, P1, P2, P2, P4 has this, right? This value, right? And it can run in parallel. Okay? It can use that resources in parallel. It doesn't matter. Whether it return or it doesn't return doesn't matter. Here, when we compute the same sequence, we assume that it will return. Okay? Because this is the worst case. What the banker is looking at is the worst case. Alright? So the worst case, we put this kind of constraint. You have to use and you have to completely return. Okay? Because otherwise, I will not grant. You understand? But once I grant, it means that you have enough resources and you don't have to worry about deadlock, because deadlock will never happen. Okay, you can use anyhow. You want to run in parallel or you want to run in sequential, it's up to you. Okay, once I grant here. Because once I grant, I already know that there is a safe sequence. Is that clear? Okay, so this deadlock avoidance is different from what we have studied before. Even though you got cyclic or whatever later on, right? Actually, you will not have cyclic case because this avoidance will prevent the cyclic Hall and wait happening. Okay, once the operating system found a safe sequence, no matter how you use the resources later on, there can never be any of the cyclic Hall and wait. So somehow it actually prevent deadlock from happening as well. You understand? Okay, so in this case here, actually the avoidance, we actually look at the resource way before the process started. And then from this auditing, we can know in advance whether it will encounter a Hall and wait cyclic manner. In this case, it definitely will never. Okay, once I found a safe sequence, this request is approved, you will never have any deadlock. Okay? So is that clear? Alright, if you miss what I said just now, I suggest that you watch the video because he also explained more or less the same like what I explained to you. Maybe it's a bit more lengthy. Okay? Now, one thing about this banker's algorithm is this. I said the banker need to find this safe sequence or safe state. Okay? You have to find this safe state. Now, if you find this safe state, then only you approve. Okay? But is it possible that it cannot find a safe state, for example? That means it go through the example and then it cannot find any safe state. Halfway it try, there's not enough available and it cannot satisfy this need matrix. Let's say, for example, just now I can strike out so many, right? I go through one by one. But suppose when I try to look at it and I cannot find anyone, halfway through I cannot go further. That means I get stuck. That means there is no safe sequence or safe state. It's unsafe. So the operating system will not grant. But is it possible that if it grants, it will run without deadlock? Yes, it may. Okay, it may, just that the operating system is being too careful. Okay, it doesn't mean that unsafe state you will encounter deadlock. No, it may not encounter deadlock, but the risk is there. Okay, so the banker will try to avoid this. When it sees that there's no safe sequence or safe state, it will not grant the request. Because if it grant, it will be unsafe and therefore it potentially have risk on deadlock. Okay? So when it grant, it means that you already know it will never encounter deadlock at all. Alright? Is that clear? Okay, you can watch this video. I have a link. I haven't added into what yet. I'll add it later. So basically, this is the banker's algorithm. Is how long? I'm not sure. It's 14 minutes there. You can watch that later on. I think, yeah, at the last part, actually, he explained what I explained to you just now as well. Okay, the link is here. Maybe I put it in straight away. Because I'm afraid that I'll forget it now. Okay, I don't have a complete slide there. I'm sorry, I've gone to the wrong place. But there's a link in the front page, okay? Where is it? Focus person algorithm. Okay, I think I'm going to add one more. additional, I changed this additional slide. Okay, I'm going to back drive this one. Okay, I did not manage to grab all the picture inside there, but you can just click on this and play the video. Okay, I think he explained quite clear there. If you don't understand, you can ask me. Okay. Okay, we move on. Okay, I'll skip this example. This example actually is the same. I mean, different example, but pretty much the same thing. Here we have a customer, but we got only one resource, which is the loan. Okay. And then here is another example with, I think also one resource as well. Here also one resource again. Okay, here it uses a different term. So if you see safe condition, unsafe condition, safe state, unsafe state, or in the video we use a sequence, safe sequence, unsafe sequence. They are talking about the same thing. Okay, just the term is different. Okay, and this is another example you can look through. You can try this exercise if you want to. So this allocation is a maximum need. Okay, and then what you need to do is find the need matrix, alright, and then find the initial available. Initial available is the total of your resources, and then subtract with this one. Is the need matrix? No, not this one. Is the allocation. Okay, you subtract with the allocation, and then you get this. Initial available, which is 332. Okay. Actually, you shouldn't put it on this column, this row there. You should put it somewhere else, because once you get the P0, you're going to add it up, just like what I do here. Okay, add it up and then put it there. Okay. Eventually, now one thing to note, if you want to find out whether your answer is correct or not, finally, when you reach here, you see this 10.5 is the same as this 10.5. Why is that so? Because everybody returned. If everybody returned, then you get back your total resources, right? So it needs to be 10.5. Okay? If you see this is not 10.5, you know that your calculation is wrong already. Okay, this one will come out in exam, so you need to know how to do this. Okay, you need to know the process. Okay, here actually shows to you the whole answer, and then this is a safe sequence. But there can be unsafe sequence. Okay, if unsafe sequence, how do you answer? Very simple. There's no safe sequence or no safe state, and therefore the operating system will not grant whatever request. Okay, it will not grant the request because it's unsafe. Alright? So that's how you avoid the deadlock. Okay, let's move on to this. Okay, this one is something different. Remember, I was talking about the 4 different conditions in order to find out whether you will encounter deadlock or not. First is mutual exclusion. You use it, and definitely that is the first condition. Second condition, you hold and wait. Okay, if you have these 2 conditions is not fulfilled yet. It doesn't mean that you have a deadlock. You might not have deadlock. You have to fulfill another. Another one is whether you can. Do you have a circular wait? You hold and wait, and then you have a circular wait. If you have circular wait, and you cannot preempt it, because after you have circular wait, you cannot preempt it. This 4 condition is satisfied, and therefore you have deadlock. Okay. Now, if let's say you can preempt the task, then you need to have a recovery algorithm. Because if you don't have recovery algorithm, you preempt and you kill the process, your data is in inconsistent state. That means it's corrupted state. And you cannot move on, and your system still is not going to run properly. Okay, even though it's get out from deadlock, but your data is corrupted. So you need a way to recover, and you have a recovery algorithm. So this algorithm, whatever terminated state, you need to be able to, first thing is, allow it to run again, successfully run again. Let me rerun the program. You terminate it, you're able to rerun again. That's the first requirement. If you can rerun again, you fulfill that. But then you need another one. Another one, you must make sure that you can roll back, meaning that whatever job has been done, database has been changed, data has been changed, you can roll back to the initial state before it has been changed. Okay, so these two requirements is needed. First, you can restart the program. Second, you can roll back your data to initial state before it gets changed. Now that is the recovery algorithm. Okay, so make sure that you're able to recover first. Then only you can implement the preemption. Okay, if you can preempt, then you can prevent it from deadlock. And this is done in database. Okay, I mentioned it many times. Database is because most of the time you encounter deadlock because you have so many distributed systems trying to use the same database, right? And so if you, let's say you take the resources and then the other is holding on it and you try to use it and you encounter deadlock. So how does the operating system recover? First you have to go and find out using the graph whether there's a deadlock. If there's a deadlock, you kill one and then you roll back. Okay, without you needing to know what is happening. You roll back and then restart your program. Okay, so because your program is restartable and it can roll back, your program actually does not suffer. It can run all over again and then it can continue to process the data successfully. Okay, only database is capable of that. Not many process is capable of this. That's why database is one of the very robust and unique program. And actually, the language is the most complex language. The SQL language is the most complex language. It's even complex than C++. Okay, the last part is starvation. And this one, I think we encountered this before, but the previous slide did not explain clearly and correctly. Right? So don't refer to that, but this one is correct. This slide, the lecturer will actually copy and paste from somewhere, I believe. This one is correct. The definition for the starvation is correct. Okay, so we have deadlock. We also have starvation. These two look almost the same, but they are different. So deadlock means they lock one another. It can be direct or it can be circular, like this. Okay, one wait for another. And they cannot progress because the hold and wait, they cannot progress. This is direct hold and wait, it cannot progress. So that is deadlock. The most serious case. Starvation is almost the same like deadlock, but it's actually not. Let's say you got resources, and or maybe one resources, but you got many process. Let's say P1, P2, P3, P4, and all of them try to use these resources. Okay, and this, let's say this P1 is a bit slow. Somehow his code is very bloated and it's kind of slow. P3, P2, P4 actually run very fast, and he tries to acquire this, and he use it, and then after that he release, and then he use it again, release, and use it again. Now, because they have to compete with one another, definitely this will lose out, right? So this guy will lose out because he's slow. Okay, he will lose out. So every time he try to grab, somebody else grab it already. So he will not have a chance to actually acquire it. So he will starve. This thread here will starve. Okay. So it appears like this guy, this P1 is deadlock. Actually, it's not, because once a while he will run. Okay, just that because he's slow, he gets starved most of the time. He does not have enough resources to use. So he'll run very slowly, okay, and starvation. Now, how do you overcome this starvation if you have this kind of problem? Now the operating system have to help, right? Have to help the process, because the process cannot help itself. Everybody who is fast is going to use first, right? And those who are slow is going to starve. Now it's not only P1, it can be other processes. So how does the operating system help these processes to be able to avoid this starvation? Okay, first thing is it provides priority. Okay, it gives priority to each one of them. Okay, so I can assign maybe this guy the highest priority, second, third, and fourth. Okay, now if this P4 used many times, his priority is going to decline. Okay, so that is called aging, the keyword down below that. So the priority is going to decline. So somehow when it declines below this P1, because the more often he uses, the faster it will decline. The priority will decline faster. Okay, so somehow P1 priority will be above P4, P3, and P2 somehow, right? Then he will have the chance to use. So that means right now the operating system, by providing this aging priority, it can prevent every one of them from starving, even the slowest one. Alright, because the more often you use, the less chance that you're given the priority to use it. So that the one that has is slow is able to use it. So right now you can prevent the starvation. So this one operating system needs to help. Starvation is something that you cannot avoid, because it depends on how the program runs. Okay, but the operating system can help by giving priority to each one of them, and the more often they use the resources, the priority will age. Age means it will decline. Okay. Okay, so that's how you avoid starvation, or prevent starvation. Okay, that's the end of this slide, and we move on to the next slide. Actually, I want to discuss lecture 7 first, but I think I don't want to delay this. I'll just continue as is, rather than bypass this P6, because lecture 7 is more appropriate to your assignment. So I'll go quickly here. I'll go quickly through this. There are a lot of slides there, and I'll skip quite a number of them. I'll tell you where I'm going to skip, especially the one that dealing with time synchronization. Okay. Okay, this chapter is about distributed process management. That means how are we going to manage the process? Okay, when they run, especially when you run in distributed manner, and you need to manage your process. Okay, because you run in distributed manner, you can actually move your resources or move your process. I shouldn't say resources, I should say process. You move your process, because most of the time your resources are physical. You cannot move it around easily, but you can move your process around. So how do you manage all this? So that is the distributed process management. Okay, first thing is what are the choices of scheduling algorithm that we use in order to manage this? And then how do we coordinate this in distributed manner? Okay. Okay, first thing is we need to know about this distributed scheduler. That means how you schedule your process running in distributed manner. Okay, and most of the time in distributed manner you will have to involve network. So you involve local area network or wide area network. Okay, the first thing in mind when we talk about distributed process management is process migration, because we cannot move resources around. Most of the time the resources are physical, so we cannot move them easily. But what we can move is the process. That's why I was talking about this. We talk about process migration. So we can move the process to the resources, right? And of course we can move the resources physically as well. but that needs people to move it, right? And you cannot do it fast, but you can move a process easily. Sorry, I shouldn't say easily. It's faster. Okay, it's not easy, but it's faster. So how do we migrate the process? Because when the program starts to run, it has states. Okay, you have to keep track of the state, and you have to keep track of the data that it has been doing. And when it communicates, how does the other parties know that he has been migrated? Because when you migrate, it goes to another address, right? So the other parties need to know, keep track of where he goes to, right? So these are the management that the operating system needs to provide, or the process itself needs to provide. Okay, so the process migration, the definition is you transfer itself to another place. That is not replication. Replication, that means you have duplicate copy and it run on both sides. This one is different. Yes, it copy itself, but once it completely copy, the original source is removed. Okay, that means the original source of the machine that it ran before, the program will be removed from there when it get transferred to another computer. Okay, the motivation behind this program process migration, of course, first thing is load sharing. Okay, if let's say I have one computer, let's say this computer, 100 people is using this computer. Let's say cloud service, right? Cloud service, I can loan this server to run multiple processes. So if you use Colab, for example, I'll be using this computer. Maybe you're sharing with me also. I also don't know, right? So it depends on Google. Google actually do this process migration behind the scene. So maybe 100 people are using one machine, but there are other machines that is idle, not doing anything. So isn't that good that we transfer or migrate some of the process to another machine? Yes, it is, right? So that's load sharing. Okay, we share the load. I have a lot of load here. You are idle, so I give to you, right? But then when I do this process migration, do I need to tell the user, hey, I have to migrate, stop what you're doing? And then we start all over again. And the fellow was like, oh my God, I'm not going to use this service, isn't it? Okay, that's why we need a system to migrate automatically without the user realizing it, okay, or aware of this happening. Okay, so that is load sharing. And another thing is, if let's say it's overloaded, it cannot respond quickly, right? Because it's overloaded doing something else, something that you're asking to process, quite a lot of work. So it cannot respond to you quickly. The responsive time is going to slow down. So this will improve your communication if let's say it is underloaded. Okay. Now the third one is sometimes your PC fail. When it fails, to you is unavailable, right? The system failed. The PC, maybe the hard disk crash, for example, or somebody cut the wire, maybe the electrical wire. So it failed. So it's non-available at the moment, right? So how do you make it available? You also migrate, right? Okay, so let's say for example, I think you must have heard cloud services promise you 99.99999% uptime, 0.00001 downtime. What it means is availability. Okay, because it can be something like this: power cut, and then your system is down, but is 0.00001% downtime, meaning that once you see the cut, immediately you see it's available again, right? Because the process immediately get transferred to another PC quickly, and then it get run. Okay. Imagine that if let's say there's a maintenance worker intervention, a fail, right? Then you call up, and then the fellow say, okay, I go and have a look. It takes 1 hour. Then I process transfer another hour, 2 hours then. So the downtime is long. So it's never going to be 0.0001%, right? It will be more than maybe 10% maybe, or maybe 20%. So they cannot guarantee you this, okay? So in order to create this high availability, you need to have this process migration in place, okay, by the operating system. Whenever there is any hiccup, it can actually migrate immediately. So that is availability. The last one is the resources, utilizing the resources or utilizing the special capabilities. For example, here, when I run, I don't have GPU. But then when I need GPU, the system will transfer itself to, or migrate itself to another PC which has GPU. Okay? At the moment, Colette do not have this service yet. I have to shut down, I have to move on to the other computer, and I can see it. And whatever process that is running is terminated, I have to restart all over again. Okay, so Google do not have this. It has this special capability, but it's not transparent, meaning that I'm aware of the transfer. Okay, because you asked me, the current computer don't have GPU. You need to migrate to a GPU, but your runtime, that means your data that you have, that you process, is going to be deleted. Is it okay? Then I have to click OK. Once I click OK, you get transferred to another computer, and then I run all over. Okay, so it's not smooth, but it's there, almost there. Okay, it gets transferred very quickly. Once I click yes, it gets transferred immediately to the GPU computer. So the last one is quite useful. For example, if you need to have GPU, then you can get transfer. Or you need to use printer, you get transfer as well. Or if, let's say, you work in medical institution, maybe the computer is connected to expensive machine located maybe in Japan only. So while you're working here, you cannot use the resources. Then when you need it, you get transferred automatically to Japan server, and then use the machine that is attached to the computer and collect data maybe. Okay, so that is utilizing special capabilities by migrating your process to the machine that is close to the resources that you have. Okay. Okay, this one already explained. I skipped it. Okay, of course, when we talk about migration, it sounds very good, right? But we have issues also, right? It's not as easy as what I say. So issues is, how do we do it? How do we initiate this migration? So we have to answer a few questions there. For it to work, we need to find out who actually initiate this migration. Is it the process or the operating system? Okay. Second thing is, what is involved when you do the migration? Okay. What are transferred, and who is involved? And the third one is what portion of the process is transferred? Because you might have gigabytes data. Do you transfer the whole thing? Or how do you do it? If let's say you want to transfer them, okay? Do you transfer a portion or you transfer all? Okay, another thing is the last one. If you are communicating with other machine, when your process move, your IP address also change, right? So how do you tell the other process that is communicating with you using your IP address, your old IP address, so that it knows that you are moving to another place and it can redirect to the correct destination? Okay? So this needs to be answered before we're able to do this migration properly. Okay? For example, while you're communicating halfway, the message is still coming, right? And then you get migrated. Is this message going to be dropped? No, right? It can be something like this. To mitigate it, you transfer, but when you transfer, you run there. Here it's still running. It's still collecting the remaining messages. Collect and then divert it to the final destination. So it's still alive for that period of time. Until you feel that, okay, right now I think I'm safe, there's no more messages, then I can shut down. Okay, so these are the issues that you need to handle in order to make sure that everything might run smoothly. Okay? Okay, who initiate the migration? As I said before, it can be OS initiated or process initiated. Most of the time, OS initiate because it has certain motive. The motive is, I need to balance the computer, right? For example, this computer is too overloaded. There's idle PC, right? So the operating system will move the process to other idle machine because the objective is to load balance. Okay. So this process normally should be as transparent as possible. Okay, it may be transparent, it might not be transparent, just like the cola. Okay, some part is transparent, but some part is not transparent. Okay, and the second what I call it system that can initiate this is the process itself. Okay, for the process to initiate, most of the time the motive is because the resource is not available. Okay, so it needs to go to Japan, for example. So it migrates itself to Japan to use the machine there. In this case, the operating system will not know. The operating system will not know, hey, you want these resources. So only the process will know. The process will know what it wants, right? So it will migrate itself when it needs certain resources because it knows where the resources is. So this is a process initiate migration, meaning that the process itself do the migration. Of course, we want OS to do it for us because it's easy. Okay, the process do not need to do it. But sometimes we need the process to do it because the OS don't know where the resources is. So it has to do it itself. And this one, the developer for this process needs to know how to do the migration. And of course, in order to do this, it needs to know where the resources in the distributed system. Okay. Okay, so what is involved when you do the migration? Do you destroy the source system after you do the migration and create it on another system? But take note that this is not replication. Is migration means you move and you shut down. You must shut down your the process in the source system. Okay, so it's a process movement, not replication. Okay, so the two things that you move most of the time is the image. That means process image. That means the code of the process. And then you also move the data. Here it did not mention it, but the data is also important. So first is the code that you migrate, and the large part of the data is the data itself. Okay, you move the data. So this is one example how we migrate. For example, in this case here, we want to migrate process tree. The reason we migrate may be because here you need to communicate with this tree, and this is very far away. So it's better that you move so that you communicate only with two. Maybe you communicate with this tree very often. So the operating system or the process itself decided to move to machine D in order to better optimize the system. Okay, so that there is less communication that is happening. Okay, this is one simple example. Okay, so what are the technique that we have in order to do the migration? Okay, so there are many strategies. Remember, when we move, we have a lot of problem, right? First thing is, do we move all or we move partially? Okay, and we move partially. Eventually, we have to move all. But how do we move them? That is the thing that we want to discuss here. Okay, so when we move, now you mentioned about the code and also the data, right? And we got here it shows actually there are more than this. Here it shows only 5. So we got eager all, pre-copy, eagerity, copy on reference, flushing. So what are they? Eager all is the simplest. What you do is you transfer the entire process image, including the data, all over to another machine. So while you're transferring, you stop the program. While you're stopping, the program is not responsive to anything. That means the user use halfway, and then you have to wait for 1 minute because the process is migrating. Okay, so this is the easiest of all. Is eager all. You transfer and you pause the program. While you're pausing, the user might be able to observe or experience that pause. That frozen time is going to be long. If let's say the data transfer is long. Okay, So this is complete transfer. It transfers the whole thing. Maybe gigabytes of data get transferred. All right. So it can take minutes, or it can take a couple of hours, maybe. Okay, depending on how long the transfer takes place. Okay, it might not be good. So that's why we have another scheme. It's called pre-copy. So how does a pre-copy works? In pre-copy, the process continues to execute while the data is transferred to another machine. Okay, so it keeps on transferring. It is still running here on this machine. It transfer. Okay, once it's transferred, maybe the process also get transferred as well. It's not running here anymore. It get run on another machine, but it's still transferring. Okay, and of course, when you're running, you will change some of the data, right? If you already transferred earlier on, the data is changed right now. You have to transfer again. Okay, what is good about this pre-copy? Pre-copy is because you're transferring while you're running, the user don't feel anything. It doesn't feel the frozen. It doesn't experience that frozen time. Okay, because you are transferring while you are running. Okay, but then the disadvantage here is if your program change some part of the data that has been transferred, you have to transfer again. Okay, so you might be transferring more than eager or all. But from user perspective, it's much more what do you call it? It's much smoother compared to eager all, because eager all, the user have to wait. Here you don't have to wait. Okay. So it reduces the time that is experienced by the user. That is, the program is frozen. Okay, there's another one, another technique. This is to solve the previous problem. Is eager-dirty. Eager-dirty is similar like pre-copy, but you only transfer the modified one. Okay, so when you modify, you get transferred. You modify, you get transferred. Okay, so you only transfer the modified one. Okay, that means that is going to be the first priority. You get transferred. So it will give you less chance of copying data, and then it get change, and then you have to copy again, right? Because if let's say you touch one memory, right? You touch one memory, that means it's dirty. That's why it's called eager-dirty. You touch, it means dirty, and then you get transferred. Now, when you get transferred, when you use the data, you use at the destination. It will not use from the source. Okay, so you transfer only once, the one that is dirty. Okay, and eventually, of course, all will get moved, but the high priority one, you will transfer the one that has been touched often. Okay, so this one is something similar like pre-copy, but then it looks at the one that has been modified. The one that is modified is the one that get transferred on demand. Okay, I mean this is on demand. Okay, the fourth one is copy on reference. This is a variation of eager-dirty. The difference is this: if let's say the computer reference the data, right? When it references the data is copied over. Okay, only when the data is referenced, then it's copied over. Okay. So this will give you the low initial cost because you transfer only what is needed on demand. Meaning that if I have a program, let's say for example, why this is useful, copy on reference. Imagine that you have a program that is this big and the data is this big. This program that you run is only this part here. The data that you use is only this part here. Right? And maybe this one is just 1% of the whole thing, and this one maybe 10% of the whole data. Okay? And because this program is only using this, so this one is the one that is copied over first. Because most of the time you'll be running this. Why copy this at first. You don't copy that. You copy the one that is being used very often. That's why copy on reference has the lowest initial cost of process migration. Because when you migrate, is this small part of the code that is running most often, right? Not? And it's very responsive because you left behind the one that is untouched one. When you touch, then it starts to transfer. When you touch, it gets transferred, right? So this is a copy on reference. Okay, the last one is flushing. Flushing is actually a technique that is used for virtual memory. What it does is this: the page that is accessed. Let's say, for example, I got this virtual memory, and then I got the storage. Remember, the virtual memory. What does it do? It actually gives the illusion that your virtual memory is big, but your physical memory is actually very small. This is a physical memory. Oh, sorry, physical. Your physical memory is small, but your virtual memory is big. Where all this memory come from? This memory actually is stored inside the secondary storage. Okay, so you page in, page out in order to appear to the program as a big memory, right? Okay, what you can do is this: if let's say not enough memory, you have to eventually save it into this storage, right? So when you store in this storage, if let's say you are transferring, there's another machine here. Okay, this is one machine, and there's another machine. It has its own virtual machine and physical memory. Instead of load it back into this virtual memory, you load it into another machine, virtual memory, and then you run there. Okay, this one is a bit cleaner, right? Because you don't have enough memory, you save into here. Okay, eventually you load it back into there, right? It's the same thing as you load it back here also, right? Just that you load into another machine rather than into your same machine. So this is flushing. Okay. So you can use flushing to hold the migrated process temporarily in the storage, and because all the computer can access this storage anywhere in the world, so it can actually load it back into this memory rather than to this machine rather than this machine, and it will be running there. Okay, and here actually, of course, the user will experience the slowdown because it does not have enough memory. It gets saved into the storage, right? But then this comes for free because even you have to suffer this. Okay, because not enough memory. But then you don't suffer when you transfer because the effect is the same. I load it back and I load it back into another machine. It's the same slow process that the user have to experience, right? So that slow process it comes for free. That means you fully utilize the slow process to transfer the data to another machine. Okay. Okay, so that's all that we have for the strategy and how we move the process across. And of course, we don't discuss how we do it in code. But then we have a system in place. Some of the cloud services actually have this kind of process in place in order to service the customer transparently. Okay. Now the last part, maybe, I think this is the last part. The last part of that problem is how we handle the message. Remember the message that is incoming? We can temporarily store the outstanding message on the source machine, and the source machine is still running the old program. It waits for the data to correct and then redirect it to the new destination. Okay, so it's forwarding it to it. Once it knows, you feel like, okay, I think every of the outstanding message is over already. Now it can safely shut down the program running on the source and then move everything to the destination machine. Okay, coming back to this migration, who actually decide? Remember I mentioned to you the OS or the process decide to migrate. Okay, the decision by the OS is quite clear. Is most of the time is because it has to load balance, Okay, so it has to decide how to balance or load sharing the resources that's available, which is the CPU. Whereas for the process, it has to decide whether it has to use the resources available elsewhere. That's why I have to do migration. Okay. So the decision to migrate is done by the OS or the process, but then we also need to look at a little bit more detail about the negotiation when you do the migration. So there's some kind of policy that's happening. There's a starter utility to start the migration. This picture here shows it. The destination process maybe is this one. Okay, it has its own starter code, and this also has a starter code which it will initiate. You ask the other machine, are you willing to take this process P? Okay, then you look at the resources and you respond yes or no. If you respond yes, then you offer the P and you accept it. And when the transfer complete, then the process is running on the new machine. Okay, so of course this will happen for all the strategy that we talk about, like eager all, eager dirty. We have this starter to actually start it. All right. How actually the strategy that you use to transfer depends on what we discussed before, but this is the initial part where you have to discuss between the two machines whether it wants to accept or refuse. Okay, because this machine can accept or refuse depending on its own policy. Okay. Okay, so this is the one I mentioned. The destination might refuse to accept. So if you refuse to accept, then you might find another computer or machine to migrate to. Okay, this one mostly depend on the policy. For example, the policy is once you finish your quota, you cannot use anymore. Okay, so the other machine might negotiate with your machine and find out where your credential, and also find out whether you have enough credits. If you don't have enough credits, you might refuse to do the migration. Okay, or maybe you don't have the authority. Let's say you're not the only COO able to use the machine. Now this machine try to migrate, it cannot migrate because it does not have the privilege. Okay, because maybe the user is not authorized to use it. So it has its own policy and it can evict it. Okay. Okay, so when we do the transfer, we also have to look at whether the process can be preempted or not. That's why we see there's checkpoint just now. I did not discuss, I forgot to discuss about that. Checkpoint. What it means is this: when I transfer, some of the program, because it's too complex to ensure successful process migration. So that's why we've got preemptive and non-preemptive transfer. Preemptive transfer, of course, is the most robust one. The other one is non-preemptive transfer. But how do we transfer? Let's say we cannot preempt that. So we use checkpoint. So that means the program have to run until a certain point. So this is a checkpoint. This checkpoint is the point where it is the easiest to do all the transfer. Because maybe at this point here, your data is already in the hard disk maybe. Okay? There's nobody else that you're communicating with. Now is the best time that you do the transfer. Transfer now. At this point, because it's the easiest. Okay? So the checkpoint normally is a point where you find that everything that you have done not in process. Okay? That means not running to completion already. So when you reach this point. So at this checkpoint, you do the transfer because it's the easiest of all. Okay, so maybe your code, this is the checkpoint. Here, not a good point to transfer. Maybe here is another checkpoint. Here, another checkpoint. So you run until the checkpoint, then you transfer. So you wait until you reach this checkpoint, then only transfer. Okay, so that is non-preemptive transfer. Preemptive, you can transfer at any time. And that one is a bit more difficult because, for example, here, in this place, I'm still modifying the database. If let's say I preempt it, I transfer. Now the code needs to rerun again. Some part of code needs to rerun. So I have to roll back. So that means when I preempt, I need to make sure that the database can be rolled back, and this program can be restarted from where it get preempted. Okay, so it can be quite tedious. At this checkpoint, we make sure that the database are all complete already when we reach here. Right? So when we transfer ourselves or migrate ourselves to another place, this database is actually in consistent state. It's not in modification state. Okay. Okay. Here actually discuss more about the timing, how you do the coordination. I will not go through this because this slide is too short, and actually it's more to this. To explain this is quite lengthy. I will skip this. He used this example to explain the problem, but I will skip this as well because I will skip the first part. Okay, and this one and this one. Okay, this is a snapshot that I was talking about. You take a snapshot. If let's say for example you modify the database. You take a snapshot first before you modify. Okay, because if you preempt, you know the earlier state, so you can revert to the earlier state. Okay, so database use rollback, but in your program you can take snapshot of your data. Okay, before you do the modification, so that when you have to roll back, when you get transferred, you can do that easily. Okay. So I skip all that and we move on to this keyword here. Actually, this keyword is just explaining something that is kind of similar, but there is minor differences there. Okay, I use this keyword quite a lot just now, load balance, right? And also load sharing. It seems like these two is more or less the same. Okay, what does load balance mean? Load balance means the system try to balance the resources that are available. Okay, if this is overloaded, you try to load balance so that they are more or less equal. Okay, this is to remove the stress from each computer, because when you load balance, here will not be overloaded. Okay, so you process at cooler what do you call it, environment, because your machine do not have to work very hard. Okay, and maybe it does not use so much power, and also the hard disk also will not run so often, right? So you can actually extend the maintenance period by load balancing. Okay, how about load sharing? Load sharing is something similar like load balancing, but load sharing is the process itself wanting the process to be shared. Okay, it has nothing to do with the optimization. Okay, so it knows that it has to work. Okay, and if you want to run fast, I load share. Okay, so I'll split the task to multiple machines. So I have a lot of tasks here. I share the task. The objective is, if I share the task, all of them will run in parallel, right? So I can gain the performance. Okay, I receive this performance gain. So the load sharing, the main objective is also sharing the data and sharing the load, but the objective is to increase the performance because we can run it in parallel. Whereas load balancing, the objective is not this, although we can achieve this as well, but it's more towards maintaining the asset such that it does not damage too fast. Okay, because we can move things around to underload the system. If we underload the system runs faster also, right? But the main objective is to make sure that the system runs in optimal state. I should say that. Okay, optimal state. So load balancing is to run at optimal state. the main objective. Okay? Load sharing is almost the same. You actually split the task as well, but the objective is to increase the performance. Is that correct? Okay, so that is the difference between the two. Okay, if you see that term, it means this. So the distributed operating system can do both. It can do load sharing because it wants to increase the performance, or it can do load balancing because it wants to run at optimal state rather than non-optimal state. Okay, now we've changed gear. We're going to move on to deadlock again, deadlock prevention. We have learned resource ordering to prevent deadlock, right? Resource ordering means how you acquire the resources, or how do you acquire the mutex. You acquire A, B, C, okay, or AC. You don't acquire C, B, okay, you acquire in ascending order. So that will prevent you from deadlock because you break the cyclic hold and wait, okay. So that's the first way. That is deadlock prevention. Another way is deadlock avoidance using Banker's algorithm. Okay. Now the third one, which we never discussed, this one is mostly used by database. Database has another deadlock prevention scheme, and it's called weight die scheme and wound weight. Actually, the spelling is wrong there. Can I? Oh, this one cannot. This one is PDF. Yeah, it's PDF. I think the spelling is wrong. It's not wood weight, it's wound weight. But I think some website it will spell wood rather than wound. The correct term is actually wound, not weight. Wound weight. And the reason why it's called wound is because somebody will get killed. It's wounded. Okay, so that's why it's wound weight. Okay, the operating system, the database actually can implement any one of them. Okay, so so the deadlock prevention, what we have learned before, that we use here, do not care about the time. Okay, but then for database, time is important. Who actually access first? Because it's distributed system, right? If I access this, I'm the one that should use first, right? Okay, and actually a large part there, because I missed the top part where actually talk about the time stamp and all that, how you keep track of the time. But imagine that you're able to keep track of the time. So the database knows who actually requests for the resources first. So you have a timestamp there. Okay. Now because of this timestamp, even though the process acquire in the correct order, because the requests come at different time, you can encounter deadlock. What I mean is this. For database, because database, not only database, database is one of the example. Any distributed system, you have to ensure this time, because let's say for example, I acquire A, acquire B. Okay? But then in distributed system, you have to send this message, right? When you acquire, you have to send a message. Now, if this message, let's say this one happened first, of course in my code, I run this one first and I run this. But as the message is sent, the machine that is received, maybe it received B first. Then only you receive A. Now you have deadlock, right? Because right now, when you acquire it in the wrong sequence. Although in my code is correct sequence. That's why we have to timestamp it, stamp the time. But when we timestamp, now we have to worry about others as well, because others, they have their own timestamp. Is our time synchronized or not? Okay, so that's why the synchronization is quite important. That is discussed earlier on. But assume that right now, our our timestamp is synchronized. That means this guy is synchronized with others. Okay. So here, when we when we receive the message, we will receive in different order. Okay. So when we receive in order, if we receive this first, we will approve this acquisition. But then later on, when we discover, actually this timestamp is before. We already approve here, and he's already doing something to it, right? Now this one comes. Actually, I should approve this one first rather than this. Okay? So how do you overcome this? Because you're going to encounter the log. Okay? So and this mostly is database. Database actually is the distributed system or the distributed system. So you have to use this scheme. Either this scheme here, wait dice scheme, or wound wait. Just because the arrival time is different from the timestamp. Okay? So maybe you approve and then, but you look at the timestamp, this actually happened before than this. But this one arrived first. So what happened? So you do this. You look at the request, the time. If P2 already acquire help by it, all right? In this scheme, it choose the older process, okay, with the older timestamp, will have to wait. If let's say it requested, so it requests, let's say P2 requests at time 10, and then P1 is 5. Okay, then P1 will have to wait. Okay, it will have to wait for P2 to complete. Okay. Now, if let's say P3 comes and P2 is holding it, now P3 is going to be rolled back. Okay, because P3 is actually has a timestamp which is 15 seconds. This is a wait die scheme. Okay, so it depends on who comes first, and also the timestamp, and looking by the timestamp, it will adjust itself to make it right. Okay, so wait die scheme actually requires some rollback, because you can see here this task here is going to be killed, and then it is going to roll back the database or your data. Okay, in wound wait is slightly different. In wound wait, P1 request for the resource held by P2. P1 is 5. That means the time frame is 5. Okay, this is how you look at it. This is the time. The time move forward, right? So this time 5, time 10, time 15. Okay? So this is the old one. This one is the latest one. Okay? The timestamp 5 will start first, time 10, time 15. So this old is latest. So that's why you can see young and old just now, right? So if P1 is younger than PJ, is going to be waiting. Otherwise, is going to roll back. Okay, so you can see here P1 requests a resource held by P2, and P1 is 5. 5 is older than 10, right? Okay, then the resource will be preempted by P2, and P2 will be rolled back. So that means this guy hold onto it. Okay, so but this guy is actually the earlier one. He requests, for example, in this case here, so you have to kill this and then roll back. Allow this process to run. Okay, so that is a wound wait scheme. If the P3 is requesting for the resources that is held by P2, and P3 is the latest, in this case he has to wait. Okay, because it's correct path. For example, in this case, if you look at this case here, if I send, okay, B arrive first, and then it hold. It is 10, is hold. But A actually should get it right. It happens before. So the timestamp is before. It's 5. So when you receive it, it knows that this guy shouldn't use it. It's this guy should use it. So he has to kill this guy, roll back, and pass it to this this timestamp, I mean this process to run. So this process is running because it actually acquire first. Okay. Now how about the other process, which is timestamp 15? That one is correct order because it hold, right? And this guy is also wanting it, but it's in correct order, so it's going to wait. Okay. So if this guy is requesting, you kill, you give to this. If this guy is requesting and this guy is holding, you'll wait. This guy will wait because it's correct. Okay. The example is like what I showed to you here. Okay. So that is a wound wait scheme. Alright, so I'm going to skip this because this one is just explaining how to identify the wait for graph. And it has nothing to do with this. Okay, I'm going to skip quite a lot of here because I'm not going to talk about this. Okay, here is election algorithm. Is just, there are many here. The Boolean algorithm, there's a ring algorithm, and then the final one is, I think, is Byzantine message. Ring algorithm, Byzantine fork communication, which is using Byzantine general problem. Okay, I'm not going to discuss because they are all, I think they are different algorithm, and it's kind of complex to explain, especially this Byzantine algorithm. And I don't see any relation to what we discussed before. Okay, so I'm going to skip this election, Boolean algorithm, and ring algorithm and Byzantine algorithm. Okay, I finish here, and this one will not come out in exam. Okay. Three 302.161. 302.616. Sorry, 302.616. Yeah, you can go ahead.